All right, so this is take 2. You don't want to see take 1, trust me. My last class, they were pretending to be a inpatients in a trauma recovery ward. So it was not pretty. Okay, so let's begin. This is a review of chapter 6, and what I'm going to do is I'm going to talk about chapter 7 just to show you that if you don't know chapter 6, you can't do chapter 7. So a couple of things that are left on the board from the last video I'll talk about briefly. You need to do vocabulary. So there will be a matching section on the test where you have to identify what terms go with what ideas, such as ionization, energy, metal, non-metal group, periodic law. There are many more. Those are just a few of them. I didn't put on all of them. So that's going to be very important. Yes. Not only do you have to know the definition of the periodic law, they might give you an application, and you have to identify that application as being based upon periodic law. Can anybody tell me what periodic law is? No? Lauren's back there shaking her head. You should know what periodic law is. Maybe you want to look it up. You guys have textbooks, you know. Annabelle from Canada, my star. She's one of my star students, and she doesn't. English is not her first language. French is her first language, and she's one of my best students. Here she is. This is Annabelle. Yes.
When electrons are arranged in order of increasing atomic number, there's a periodic repetition of their physical and chemistry properties.
Correct.
So
Good.
it's basically that there's column and there's always the same pattern of properties.
There's a repetition of properties based upon increase in atomic number across a period. Exactly. That's exactly what it is. And who kind of started that idea, but based it on increasing atomic weights? It was a very simple... Yeah, Mendeleev. It was kind of a simple... but based on what he had to work with, which was pretty much nothing. But was he the first one to discover the existence of elements? No, they knew about certain elements for many, many hundreds of years. And gold, that's a very good example, actually. Gold's a very good example. But what he did was, he was the one who saw that there is a repetition of properties every so many increases in atomic weight. Yeah. And then the modern periodic law is based on repetitions of properties based on increases in atomic number. Yes. And atomic number, why would the atomic number be more modern than Mendeleev? And Mendeleev lived in the mid-19th century. Anybody got any years on his birth and death there, Mendeleev, Professor Mendeleev? The Russian guy? We just call him the Russian guy is what we call him. We're just very familiar with, he's a friend of ours actually. 1829
to 1869.
1869, so he's definitely mid-19th century. Is that not him?
Because I went over the book and there wasn't any date that I was looking for.
Okay, so who did you just give me the birth and date of?
That
Different systems for organizing the elements.
Yeah, that's when they were exposed.
That's when they started thinking of systems.
Okay, so anybody want to take out their device and quickly look up? You know, the entire world thinks that my chemistry class has no idea what they're doing. So you want to correct this, please? Yosef, you want to leave the comedy to me. You know, I'm the director, I'm the talent, I'm the producer, written by, everything, okay? But I appreciate the attempt, poor as it may have been. Yes. Anybody have the dates of his?
No,
Yeah, we're looking. All right, we'll get back to you on that. I'm still curious as to what date you gave me, Ahmed.
It's this,
This is
the,
the thing about-
the periodic and the several systems to organize elements.
All right, you want to say that again?
It's the periodic time when.
It's when the-
systems have been.
It's what?
When the different systems
It's when different systems were
for
proposed.
organizing.
When different systems were proposed. So from 1830-ish to 1870-ish, we had various proposals of that led to the formation of the periodic table. Fabiana, thank God for Venezuelans. I love it. Okay, you want to tone that down there, Youssef?
So he was born on the 8th of February.
8th of February, coming up, huh? Another month.
1834.
1834. So Mendeleev was born in 1834. Excellent.
And he died the 2nd of February.
2nd of February,
1907.
1907. So he
That
lived
was
into the.
72.
He was 72. Excellent. And where was he born and died, Mustafa? Do you have that information?
He was born in
Yeah,
Russia.
he was born in Tobolsk, Russia.
Tobolsk.
Yeah, and he died in St. Petersburg.
Yeah.
He died in St. Petersburg. Do you know what the significance was of St. Petersburg in that part of the century? It was the capital, I believe. It was the Bolsheviks moved the capital to Moscow. I think that's correct. Is that correct? I think that's correct, yes. Anyway, so periodic law is going to be very important, Ahmed. You get that? Yeah, so you want to distinguish between the development of the periodic law and the men and women who set forth the proposals. That'd be an excellent idea? Excellent. Okay, good. So we have other things, group number, periods. What are the periods? Are they, they're the, no? Would you say the rows? Yes, I'm sorry, I thought you said columns. They did say rows. The columns are what do you call the columns?
Groups.
Groups, and more specifically they are the halogens, the alkali metals, the alkali earth metals. They are called families, yes. Where do the valence electrons come from? What sublevels? S and P. Excellent. You guys are much better than the last class. S and P. Excellent. Okay, you all right there? Okay. Mustafa just coughed up a fur ball. Excellent. Okay, now, sorry, Mustafa. Mustafa looks incredibly insulted. It was not meant as an insult. What else? So what is the valence shell of the sodium ion? No, listen to my words. Listen to my words. I didn't ask you what family they're in. I asked this. Are you ready? Listen carefully. What is the valence shell of the sodium ion?
S.
S.
Now, S is a subshell. What is the valence shell?
18.
No, 18 is a column. 18 is the no of the sodium ion.
1A.
I don't know.
Supposed to be B.
No, they're not getting this. Listen, listen carefully to my words. Listen carefully. Stop looking through the book. Get out your periodic table. What is the valence shell of the sodium ion? Now this is a class. While they're thinking, I'll have a talk with the audience here. I have all this posted online. It's all there. It's at the end. It's the first day of the new week. They didn't really do much over the weekend.
3 is 1.
No. The valence shell of sodium is 2. Isn't it? Doesn't sodium react and give up 1 electron? It's 3s electron to become like neon. Neon has a valence shell of 2. Therefore, the valence shell of the sodium ion must be 2. What is the valence shell of the aluminum ion?
2.
2. Excellent. What is the valence shell of the magnesium ion? 2. What comes after aluminum?
Silicon.
Silicon. Excellent. What's the valence shell of the silicon ion that is +4?
Oh, it could be 2 or...
No, it's +4. What is the valence shell of the silicon ion that's +4?
3.
2.
2. What is the valence shell of the silicon ion that has a -4 charge? 3. What is the valence shell of the phosphorus ion?
3.
3. What is the valence shell of the fluorine ion?
3.
What is
No.
What? 2.
2. What is larger, the aluminum ion or sodium ion, and why?
Sodium ion.
Why?
Because of
He said the sodium ion was larger than the aluminum ion. Excellent, but why?
electromagnetic pull with the electrons and the nucleus.
It's radius.
It's
Yeah, but
because
why?
It has less proton.
because electrons are negatively charged and protons are
Positively charged. Excellent. So why wouldn't sodium be smaller than aluminum?
because aluminum has more electrons and more protons. So
They both have the same number. How many electrons? How many total electrons does the aluminum ion have?
13.
No. He said 13. That's incorrect. The aluminum ion.
Ew.
27.
No.
27.
No. What is the charge of aluminum? What's the charge of the aluminum ion?
+3.
+3. Excellent. And why is it +3?
Because it gave up 3.
It gave up 3 electrons. So how many electrons does it have? If it had 13 electrons and it gave up 3, how many would it have? 10. Excellent. How many electrons does the sodium ion have?
10.
No.
10. How many electrons does the silicon +4 ion have?
10.
10. How many electrons do sodium, magnesium, aluminum, and silicon +4 all have? 10. What has the larger nuclear charge? Silicon +4 or sodium +1?
Can you repeat?
Silicon +4.
You're correct. Silicon +4 has the larger nuclear charge. What is the nuclear charge of silicon +4?
+4.
No. +4 is the charge of the silicon ion. But what is the total nuclear charge of the silicon element, the silicon ion? 14. +14. Why is it +14?
Because there's
14 protons.
14 protons. And how do you know there's 14 protons?
Because of the atomic number.
Because of the atomic number, which is the number of protons. So what has the larger nuclear charge? Silicon +4 or sodium +1? Silicon +4. Therefore, if they both have the same valence shell and you didn't enter into it anything that's going to affect the radius of that ion, such as the nuclear charge, they would have the same radius, right? But because silicon has a significantly, 14 is significantly larger than 11, silicon has a significantly larger nuclear charge, what does that do to the radius? Does it shrink the radius or does it expand the radius? It shrinks the radius. So what has a larger radius, sodium or silicon?
Sodium.
Larger.
Sodium. So why is sodium, now that we get just right back, that's exactly what Mustafa said. It was sodium was larger. But now, Mustafa, explain why sodium is larger than silicon. It has a smaller nuclear charge.
And smaller.
It has it has a larger radius. Sodium has a larger radius than silicon because only it has a smaller nuclear charge. Do you understand? You're sure? Now, where could you find this information other than in the book?
The internet.
On the videos that I made?
Yeah.
True.
Just spitballing this, you guys, do you think?
Yeah.
Okay, excellent. So now, what are you smiling at?
Nothing's there.
Nothing. Okay. So anyway, so that's something that you have to know. You have to know the ionic radius and the series. What's a larger ionic radius? Phosphorus or sodium? And why? What has a larger ionic radius? Phosphorus or sodium? Yes. Sodium is larger than phosphorus?
No.
What is the valence shell of phosphorus, sulfur, and chlorine ions?
Didn't you say larger
Phosphorus
radius?
is 3.
3.
Did I say larger radius?
Phosphorus, sulfur, and chlorine.
Yeah, the larger.
Yeah.
What's larger, phosphorus or sodium ion? You said sodium.
Yeah, because I thought the radius of that was bigger than the.
Increases and it's
No.
bigger because the size
No.
increases.
No. What's larger? What's the valence shell of the phosphorus ion? Yes.
3.
3. What's the valence shell of the sodium ion? 2. So how could an atom, an ion, with a valence shell of 3 be smaller than sodium, which has a valence shell of 2?
The shells
I
are
got confused
closer.
because you said the radius. So,
I did say the radius.
so.
What has a
It has
larger
more
what has a larger radius? No, but what is the atomic radius dependent upon? If you're comparing two ions that have a valence shell of 2,
Charge.
then it would be dependent upon the charge. Yes?
Charge.
But if you're comparing two ions with different valence shells, what would the ionic radius be based upon to a larger degree?
The size of the valence shells?
The number of the valence shell.
Yeah.
So 3 would be larger than 2. So therefore, phosphorus would be larger than sodium because phosphorus has a valence shell of 3 and sodium has a valence shell of 2. Now, what's larger, phosphorus or chlorine?
Phosphorus.
Chlorine.
No, phosphorus is bigger. Because chlorine has more electrons and protons, so
It has more. No. It does not have more electrons. The ion. Yes, it has more. Yes. Yes. Chlorine has a greater nuclear charge, but what has more electrons, phosphorus or chlorine? The ion.
Both have the same.
Yes, very good, Youssef. Exactly. They both have the same. Remember. We don't mention the octet rule in here because it's not really the octet rule that's important. What's important is they want to transition to a valence like the nearest noble gas because the noble gases are what? Are stable. You can't really use the octet rule because what about helium? It's not a question of whether or not the octet rule. Yeah, the octet rule is a good rule of thumb, yes. But what's the deeper reason? The deeper reason is because it wants to get to and have the more stable electron configuration. And the more stable electron configuration is the nearest noble gas. So it will either lose or gain electrons based upon that premise.
configuration of a
Correct. Yes? So you're going to have to know, you're going to have to recognize what elements an electron configuration is written for. You're also going to have to know about ionization energies. We talked about atomic radius. Well, we didn't really mention atomic radius. How would atomic radius vary as you go down a column? You go down a group. Would it get larger or smaller, the atoms?
larger.
Much larger, correct. How about if you're in one period going from left to right? They would get smaller based on the fact that the atoms all have the same valence shell, but they have increasing numbers of protons. The nuclear charge is increasing, so it's going to cave in, right? That valence shell. Let me ask you this. What has a larger first ionization energy? Magnesium or aluminum? What has a larger ionization energy?
Aluminum.
Magnesium or aluminum?
Aluminum. It says 578 on aluminum and 700. What?
That's
No.
energy.
Magnesium has.
Magnesium.
It's
Why?
ionization energy.
Because magnesium. Okay, aluminum is
It
on
says
that
on
side of.
All right, wait. Excuse me while I yell at two students. I'll be right there. back. What has a larger ionization energy, aluminum or magnesium? Magnesium. But what would you expect? Aluminum, right? Okay. So why is aluminum lower than magnesium? Because you're removing the first p electron, correct? And what are you being left with?
S.
You're being left with a pair within the S sublevel. Yes?
Yeah.
Now, I read an article online which said, you know, this whole idea of what's left over isn't as important as the fact that you'll get a decrease in electronegativity, in ionization energies, because the aluminum atom has more electrons and shielding effects, etc. But I just don't buy their arguments, whatever the argument was. The argument is very simple, that you're getting rid of an electron that will create a more stable configuration. So you're creating a configuration that has a full S. That's very stable. Where else in a period do you have a drop in ionization energies?
Gallium.
No, but between what two groups do you have an additional drop in ionization energies? The only other example.
Other metals?
Well, no. Look at the groups. Look. Try to remember what I did in terms of ionization energies. Try to remember what the graph looks like. Remember, but tell me between what two groups do you have an additional drop?
Between transition metals and metals.
No. Think.
Sublevels.
Valence electrons. Valence electrons are S and Ps, right? Yeah, you have drops within the transition metal, but what between what two elements is it in the third period? Second and third period. Where's the drop? Where's there a drop?
Between zinc and...
No. The S and Ps, Mustafa. The S and Ps.
The
Period 3. Zinc is in period 4. I'm talking about period 2 and 3. No, you already said that. Between group 2 and group 13. Yes, correct. What is it?
Representative element?
Yeah. Yes, in group 2, in period 2 and 3. Between what two groups is there another drop in ionization energies? You're staring right at the paper. Why? I don't understand.
So,
Mustafa, give this to me, please. Is there something wrong with this table? Guys, look at nitrogen and oxygen. Isn't there a drop? 1402 to 1314. Phosphorus and sulfur, 1012 to 1000. You can't see that? Are you guys okay? Isn't there a drop between 15 and 16? Isn't there?
Yes, there is.
And how come you didn't see that?
We thought you were talking about the same drop you showed us.
No, the additional one. There's two drops. There's a drop between 2 and 13. And there's a drop between 15 and 16. Now, what's the old identification of the groups 1, 2, 13 through 18? They're called the what elements? It's a letter in there. It's a letter. Aren't they the A elements? Do you remember?
yeah.
We talked about that. And so what's in terms of A elements, what would groups 15 and 16 be? 5A and 6A, correct. So between 5A and 6A, you have this additional drop, correct? Yes? Okay. Why do you have that drop between 15 and 16? I'm going to erase this. Is that okay? Is that okay? Get another marker here. So we're going to compare. This is group 5A, and this is group 6A. Right? So we're comparing this electron in 5A with this electron in 6A. Why is it easier to remove that electron than it is to remove that electron?
Because this is closer to the middle. The one on the bottom is closer to having half-filled.
Yes. This is half-filled.
Yeah.
Half-filled is very stable. It's extremely stable. This is not easier because of what will result. This is more difficult because it's coming from a half-filled configuration, which is very stable. A half-filled P and a half-filled D are very stable configurations. When we talk about hybridization, we'll talk a lot about that type of low energy, high stability configuration. Yes? So that's why you have that. That half-filled is very stable. So that's more difficult to remove. This is not as stable. So that's easier to remove. This is not easier to remove because of what will result. This is easier to remove relative to this because this is coming out of a half-filled configuration. Do you understand that? Now, there are books that will say something contrary or something in addition, but I don't buy that. The answer is this. Look it up yourself. Yes? All right. Excuse me, sneezed. Terrible cold. I have a terrible cold. Okay, we're going to make this part 1, okay, of test review. We'll come back and wrap it up in the second one. Yes? All right.